about how we capture and measure elements of the network. This is the session where we're going to do that. I'm really happy to have Molly Copeland do this work. Molly Copeland is a Ph.D. student here in the program who's on the market next year. So those of you who are hiring, remember that she needs a job. So we'll take that contact. Molly.
Thanks, Jim. Can everybody hear me in the back? Sounds good. Okay, let me know if it's echoey or weird or whatever. So as Jim said, I am a Ph.D. candidate here in Duke Sociology, and today I'm going to be talking about whole network descriptives, or really sociocentric network descriptives. So before I get started, I wanted to say thank you and acknowledge two sources in particular: Jim's slides from class, so those have been the backbone for this, and Tom Valente's Social Networks and College textbook. I also wanted to say, as I get going, the slides are on the Dropbox. Feel free to open them and follow along, but also you'll have them later if you want to look things up. I'm also trying to have a lot of kind of practical, empirical examples of how you might encounter some of this stuff in the social networks and health literature, so you don't have to scramble to write down those citations. That'll all be in the slides, and I have a full bibliography at the end of that as well. So if you want to look things up later, that should all be available. With that, please stop at any time, interrupt me if you have any kind of questions, if you have comments or ways to extend this to your own particular research questions and subfields. We've got quite a bit of breadth here in both people's familiarity with this topic, just in terms of the network concepts, but also of what material and research questions you're going to be describing with these descriptives. So please feel free to make this as interactive as possible, because I think that'll really make it more useful. Sound good? Okay, so when we're talking about whole network descriptives, whole I think can be a bit of a misnomer, because most of the time we don't have something that's truly complete in the sense of having measured, all of the span of social relationships over time that we might expect. So what we're talking about is sociocentric network data, really as opposed to egocentric network data that you're going to learn about tomorrow morning with Rhea Perry. So the idea that we have not just information from one person or one source about their ties, but we also have information from those individuals they're tied to as well, from their alters. So the classic example might be ad health. I study adolescent networks and mental health, so you're going to hear a lot of examples about adolescent networks and mental health today. But we don't just survey one student about their friends, we surveyed everyone in the school, and then we can match it up to kind of get some kind of map or a global map of friendship relationships in a brain like this. So everything you learned this morning from Craig about thoughtful sampling and about understanding your network boundary and thinking about what is a reasonable and valid network boundary, all of that still applies for everything we're going to be talking about today. So just to give you a little bit of an overview of where we're headed, the bulk of this lecture is going to be talking about centrality measures, because I think that's really the bulk of what's considered in the literature, and that's a great starting place in thinking about these types of things. If you're new to network analysis, we're going to take a brief detour into centrality measures with two-mode networks and do a little bit of a recap about what a two-mode network is and how we might think about describing two-mode networks. Then we're going to talk about connectivity and cohesion and roles. And you can think about this too as in a kind of micro, meso, macro framework, that we're thinking about attributes of individual nodes and also the more proximal features of a social network, things like the dyadic relationship or triads. And then we can aggregate up to groups, things like cliques, and all the different ways we could measure groups and cliques. And then we can think about describing the whole network overall. So how can we talk about something like the density of an entire network? I'm not going to be framing things from this micro, meso, macro approach because I think if you are new to network analysis and you're used to a regression framework or a more qualitative framework where you're thinking about attributes of individuals, that translates most readily if you're thinking about centrality as an attribute of individuals, and then we can kind of aggregate from there. That makes sense. So centrality is asking a very simple question. How do we know who is an important node? What is an important node in our network? Or really, who's at the center of the network? But what you mean by the center very quickly gets very complicated. So for example, this is one of my favorite slides, and a total hat tip to David Scott, whose website I borrowed this from. So he constructed a periodic table of network centrality, of all the different network centrality measures that he had encountered while he was doing his PhD, and all the times they've been cited, and when they've been invented, and things like that. So just from this, you can get an idea that we're not talking about just a handful of measures. the vast universe of centrality measures of how you could say a node is at the center of a network or this node is important is hugely variable, even within centrality at all. So given this breadth of what a centrality measure can mean, today we're going to focus more on the concepts and kind of the most common ones, and really the underlying ways that you should be thinking about centrality measures, so that then you can tailor it to your specific research question, and you can go find the particular centrality measure that might be perfect for what you want to see. But I just wanted to give this caveat at the beginning that today is not going to be completely comprehensive about every centrality measure that you encounter. So to build some of this intuition about how we might distinguish important actors, centrality, what is the center of a network, can very quickly get complicated because of the network structure. So if we just have these toy example networks here, it might be very obvious in the first network there on the left who's at the center. Person A looks like they're really connecting everybody else. We've got quite the hub going on here on the left. But deciding who's at the center of the next networks might be a little more confusing. So we could say that, well, this person has the most connections, but this person's really connecting different groups in the center of the network. Or here in the circle on the line, what node would be at the center of that is not entirely intuitive. So Freeman's kind of classic foundational paper said when we're thinking about centrality, we should be thinking about a centrality measure that meets 3 criteria. First, it's something that we can calculate for individuals. So we're trying to decide which node in the network is most central. We're not talking from the start about a picture of the entire graph or a group. We're talking about individual nodes. And because of that, then we can then normalize it by network size because we might want to compare across networks. So you want to make sure that you're not just measuring something that's an artifact of how many nodes you have in your network, but it can be normalized to be comparative. And finally, that then you can come up with a centralization counterpart at the network level. So if it's something that we're saying is a property that this is an important node, this is a central node, we can look at how that importance or centrality is dispersed across the entire network so that we can compare networks that are, say, more or less hierarchical or more or less reciprocal or something like that. So these are kind of the 3 tenets of what might make a centrality measure. And Freeman came up with 3 of the probably the most common centrality measures that we're going to talk about today: degree, betweenness, and closeness, which have really been around since that paper. And we'll talk about each of them in turn. But before I do that, I wanted to, again, highlight the importance of thinking about your particular network and your data and your research question from a theoretical or conceptual perspective. And so one of the ways to do that comes from this paper in 2005 by Borgatti, where he says that thinking about what flows through the network might determine the kind of process that you expect and might determine a more appropriate or less appropriate measure. So for example, if we talk about geodesic, so that term comes up a lot in centrality measures, it just means the shortest path. So if we're talking about something that flows through our network by the shortest path, it could be something that you kind of broadcast and you can send through many times at once, or it's something that might have to move just from node to node to node. Right? Maybe it's something that doesn't move on the shortest path, but just moves any old way at once, like a random walk. Right? It might repeat back to the same kind of people. And we can think of examples of this process. So if I order something from Amazon, we expect it to take the shortest path, and it's some kind of transfer. I hope they're not sending the exact same thing to somebody else, right? I paid for it and I ordered it. And I hope it takes the shortest path possible. It better go from that Amazon warehouse to the regional post office, to my post office, to my doorstep. And if it repeats somewhere along the way, if my order is delayed, I'm going to be pretty annoyed, right? So you could think about your process in terms of how information is spreading in the network, because if you are thinking about something that moves along the geodesic, the shortest path, you might want a different kind of centrality measure than if it's something that could move in many different ways, like when you send an email to a whole bunch of people and it could move through multiple ties at one time, for example. Package delivery or gossip, right? Gossip might come back, even might be sent out through many different, or might be sent person to person in a whisper network, but then come back to the original source. So I want to introduce you to the running example that I'm going to have through most of this talk today. So this comes from the faux ad health data set that you cleaned with Maria Christina that you've been working with so far. I just took a subset of that, so I took only 7th and 8th graders just so you can have a small kind of pretty example for when we're talking about different centrality measures. So just to recap, this would be from a survey where the nodes or vertices are students, and the ties are that they said that person is my friend. So it's a friendship nomination. Because of that, it's also a directed network. So for example, this person said this person is their friend, so the arrow is pointing in that direction, but it doesn't go back the other way. So we have directed network data. It's about 35 nodes, and we'll be using that for descriptors throughout. So if we're back to this question of how can we distinguish important actors, and we're going to look at some of the main types of the way that that's been done in the literature. Again, there are many more centrality measures than just these four. Degree centrality is perhaps most common. That's simply counting up the number of ties. If you have undirected network, you're done. If you've counted up the number of ties, you have calculated the degree centrality. Sometimes you might, depending on your subfield, you might see this normalized by the size of the graph to get a more kind of normalized degree measure. I think that typically with most of our research questions, degree is so intuitive, saying this is the number of friends you have, or this is the number of sexual partners you have, that we don't bother normalizing because it's something that kind of makes sense on face value like that. So if we were to size our nodes by degree in our toy example, we'd get something like this. So we've got a few very popular people. I think the highest degree is somewhere around 15 for this. And we've got some less popular people on the edge. Because it's directed data, we can further split up degree to in degree and out degree. So we can take account of that direction. So this is sized, I believe, by in degree. And so nodes are bigger based on how many ties are coming into them, how many friendship nominations they receive. That would be their in degree. If you recall, Maria Christina, when she was making that data, very astutely pointed out that we're cutting out all of the isolates. So in most schools, there are a few kids in school who say, I don't have any friends, or my friend is, Mickey Mouse or whatever, and counting as isolates in our data most of the time. So isolates are a special case that would have a degree of 0. Or an in degree and out degree of 0, that you might want to think in particular that they could be at higher risk for some of the processes that we're interested in studying. So for example, when I'm studying adolescent depression, I might be more concerned about the kids who are saying they have no friends in their entire school. Right? But they also might be excluded from some particular kind of influence or contagious process because they're not connected in that network. So don't forget about the isolates, even though they're easy to chop out of your graph, or they have an in degree and out degree of 0. So one example of degree centrality used in the literature was a paper from Cornenko and co-authors in 2013, where they are looking at nursing students, and they survey the nursing students about their friends, and they take swabs to measure salivary cortisol, which is associated with stress. And they actually find that there's significantly higher cortisol for nursing students who have a low out degree, so those who are saying they have fewer friends in their network. They find that higher cortisol is also associated with lower and higher popularity. So there is more stress associated with being very unpopular or with being the most popular in the network. And there's kind of a sweet spot where you see a benefit to lower stress and lower cortisol from mid-range popularity. So that's also one of the only papers I can find that has a very nice degree visualization on the graphic network. So that's a great one to check out if this sounds like something that might be applicable in your work. But, I think there's always a but with every centrality measure you're going to try, degree is purely local. So degree is only measuring the local structure. It's measuring one node's ties and saying that node is particularly central in the network because of its ties. It's not taking anything into account from what's going on in the rest of the network structure when we have sociocentric network data. So degree can be kind of deceiving. In this toy example here, you'll notice that the highest degree might be somebody here who's deeply embedded in this group with a degree of 5, but we might think that this person who's linking 3 groups is playing a very important role. And it might be very important for whatever kind of contagion or diffusion process we're studying, and we might not notice that if we're thinking, degree of 3, doesn't matter, not exciting, moving on. So degree might be less appropriate if you have particularly non-local questions. And we've got some other centrality measures that might take that broader network information into account a little better. So if, for example, if we look at our toy network here that's sized by in degree, you'll notice that both of these light blue nodes have an in degree of 2, but we can tell just from looking at it that they're occupying very different places in the network. network structure, and they might have very different kinds of risks and benefits associated with their position, despite them having the same degree centrality. So another centrality measure we might want to consider is closeness. This is one you'll see probably quite a bit in a lot of at least the sociology, social networks, and health literature. So this is saying that actors are important if they are less distant to everyone else in the network. So we're going to measure their distance from every other node, and then we're going to take the inverse of that and say whoever is the least distant. I want to note that throughout I've included some of the math on these. Almost all of that comes from the Wasserman and Faust textbook, the Big Red Bible of social networks. I'm not going to get into the math most of the time because I think it's very rare that we have to calculate some of this matrix algebra by hand anymore. We're mostly just telling R, like, hey, do the closeness, and we don't really need to mess with this. So that's there if you want it, that's there if it's helpful for you, or if one day you find yourself making your own centrality measure, but don't be scared just because you see that. So closeness is based, again, on the geodesic, on this shortest path. Because of that, it's only measurable if there is a path. So if we have an isolate who's not connected to the network at all, their closeness is infinite. And you'll see when we get to the lab, when we try to run it in R is going to say, like, I don't know, it's infinite. Right? You can't measure closeness. So we can only measure closenness on a connected graph or component where each node is reachable. So we take the inverse of the sum of distances from the actor to all other actors. It's typically standardized to range from 0 to 1. So if we do this here in our little toy examples, just to, again, to give you an intuition of what R is doing for you, or theoretically what it could be doing for you, but it's now probably doing it in a much faster, more efficient way. So if we look at this example, so node 1, it is one step to every other node in the network. The other nodes are 2 steps from everybody except node 1. So we could translate this into the adjacency matrix. And then if we calculate that up, we take the inverse, we normalize it, that gives you your closeness value. So that's the intuition behind what's happening. Note that closeness is not necessarily the same as degree, right? So if we have our toy network here sized by closeness, I think this is in closeness, so you'll notice that some of the nodes kind of are so small they basically disappear during our visualization if they're not sending out degrees. Right, so even a node that was very, very popular, receiving a lot of nominations, if it didn't send them, it's going to have very low directed in closeness. And we can plot the closeness and the degree of our connected graph. And you'll see that they kind of track, but not exactly. They're not the exact same thing, right? Closeness is taking in a lot of more information if it's trying to count up your distance to everyone else in the network.
What do you mean by normalize on the
Sure. So normalized just means that when you calculate it, it's then, so G stands for all the nodes in the graph. So we just make sure it ranges between 0 and 1 so we can compare across graphs. Because you could imagine if you're counting up, I'm in a network of 100 people, and you're counting my closeness to 100 different people, versus you're in a network of 10 people, and you only get to count up your distance towards 10, right? Those are not comparable. So we're just normalizing by the size of the graph to be able to compare and to be able to make it 0 to 1. Yep. And again, R does all of that for you. That's all in there. Okay, so we could compare closeness and degree, which is a little explanation out there. Again, closeness could be directed, so if we have the directed data, we can specify in and out closeness. But, always not, centrality measures. Closeness has some problems. And in fact, we might not choose this as our optimal measure most of the time, because there's an inherent nonlinear distortion just because you're taking the inverse. That infinity problem, that distance problem, that we can't calculate this if we have 2 different graphs that aren't connected, or if we have isolates. How do we try and solve that problem? And people have come up with solutions, but the solutions are different, and there's no clear reason that one is better than the other. Sometimes it's hard to even tell how people have tried to solve that problem. So people, for example, you could treat isolates as the greatest distance plus 1. Some people would just treat it as the network size, so would substitute that in, and they're kind of ad hoc. There's no real reason to think that one of those is more principled and a better solution than the other. The other problem is that some programs, sometimes, some scientists, are not taking the inverse of the distance. They're not saying that it's a higher value means you are more close to more individuals. They're saying a higher value means there's more distance to more individuals. And in fact, a low score is indicating higher closeness. And so remember, Christina was talking about two main network packages in R, StatNet and iGraph. StatNet is doing the traditional sociological thing of taking the inverse when it measures closeness. iGraph is not. So you're going to get completely opposite measures. iGraph is saying higher numbers mean people are more distant and it kind of takes more work to get there, versus StatNet, which is saying higher numbers means you're more close, right? So it takes the inverse. And you don't know that. You just told iGraph or StatNet, hey, do the closeness, right? And it's not telling you, oh, by the way, this is the underlying matrix algebra that we use. You don't know unless you go look that up, right? So closeness can be tricky because sometimes you're getting the exact opposite of what you think you're going to be getting because of that. Any questions about that? That's kind of the word warning, right? Like some of us learn that the hard way every time we're working with StatNet or iGraph. Okay, so another of Freeman's three classic centrality measures is betweenness. This one's a little bit different from degree and closeness because it's looking at controlling the information, a node that lies on the path that connects other nodes, that's between other nodes, essentially. And so you could think of this as something like bridging. There's some argument in the literature to whether or not this is really bridging and how to better measure bridging, et cetera, but it's something akin to that at least. So it counts the number of paths for actor J, where actor J is on the shortest path for the geodesic between two other actors. So J's betweenness is the number of times that they're on the shortest path between other people. So you could think of that as somebody who might control information or have access to a lot of different types of information. You might think a lot of the betweenness literature is thinking about things like innovation, that the most opportunities for innovation arise when you're really bridging across people with different information or different norms. So one paper that has an excellent visualizations of describing these kinds of measures to a health audience and a non-network health audience in particular is from Landon and co-authors. And they're actually using bipartite data, so we'll get into that a little later on in the lecture. But they demonstrate betweenness, the idea of how many times is this node of interest on the shortest path between other nodes. And that's essentially what we're calculating betweenness. So it's taking into account a lot more network structure, a lot kind of more far-flung pieces of network structure than just degree. So if we size our nodes by betweenness, you'll notice some differences from our degree and in-degree nodes, right? So we've got a few individuals who are playing a role that's really bridging other people in the network. A few critical connectors. But betweenness, because it's only focused on the geodesic, might be almost too strict. Might be problematically restrictive because it's saying we're only interested when you're on the shortest path between other people. Our process of interest might not lie on the shortest path, right? If we're interested in the flu doesn't always just take the shortest path between everyone. It might be spreading in a much more kind of parallel duplication sense. So information centrality is the exact same idea as betweenness, except it's not restricted to the shortest path. So it's thinking that information can flow along other ties in the network that aren't necessarily the shortest path. One of the, I think the best uses of centrality measures both for kind of heuristic for yourself when you're thinking about your network data or learning about your network data and when you're describing it for other people is thinking about how these centrality measures are working in tandem and how you could really compare them. So for example, a node that has low degree and high betweenness might indicate that even though that node has a few ties, they are critical for network flow. They're really bridging different groups in the network that might be less well connected or disconnected if that individual isn't there, right? Or a node with high degree and low betweenness might have a lot of ties, but they're very redundant. And so depending on your research question or what you're thinking about as your network flow process, how these pieces are working together for different individuals may be really informative. Again, if we compare side by side our graph with in-degree and our graph with betweenness, you can see that there's some relationship, but it's not a one-to-one correlation, even though we consider both centrality measures. They're really getting at different facets of the structure. And that's what makes thinking about this theoretical underpinning that motivates your question is so important, because you can measure very different things. And in fact, in our toy network, we can compare them. So if we just make a little kind of table in R of the first 10 nodes in our network, you can look at kind of some interesting cases. So for example, we can see an individual who has a very high degree, right, but very low in degree. So they're saying, I have a lot of friends, and only 3 people are saying it back. They have very high betweenness. They have high betweenness, so right, they're fairly important for connecting others in the network, but they're not close to a lot of other people in the network, or relatively speaking, they're in mid-range, right? And we can look at the correlations between our measures. And even in our toy network, you can see how this could be informative. So for example, degree and in-degree, of course, are very highly correlated because in-degree is half of what's making up the information about degree. But something like closeness and in-degree are not necessarily correlated. So you can be very popular, but not very close to everyone in the network, right? So we might expect different clusters of density. And that's going to be part of our motivation when we're going to look at how things like degree and closeness are distributed across the entire network. I want to point out that we're just comparing measures here in one network. So we're comparing different centrality measures in one toy network for 35 nodes. So if you are comparing across networks, you might want to be thinking a lot more thoughtfully, particularly about normalization, and that you're not just picking up some artifact of the fact that you might have one really small network and one really big network. Okay, so you have to pay attention to normalization. Again, most of that's being done under the hood in R, but you want to be thoughtful in your interpretation because R is not interpreting it for you.
So in a directed network, though, is the betweenness based on the outgoing ties? And so is it sort of maybe artificially inflated if you have this perception that you're tied to a lot of people, but those ties are not being reciprocated?
Definitely. So the question was, if we have a directed network, could betweenness be inflated because you have this perception that you're really popular, you're sending a ton of outgoing ties, but maybe that's not really reflective of reality. So first of all, how you're calculating betweenness is going to the kind of default setting of whether or not it's treating that as directed or undirected, and it's in or out might depend on your program, right? So that's
specify whether to use the.
I think you can in stats. Yeah, because you can kind of say that taking direction into account or not into account and specify in different ways. I'm pretty sure, and if that's incorrect, I'll get back to you and I'll apologize to everyone for saying the wrong thing, but I'm pretty sure that you can, and I think you can see that reflected here in some sense, right? That the individuals who are very popular but have low out degree are being sized differently, right? So I unfortunately forget exactly what I did in this visualization, but I'm pretty sure you can specify. I think that question almost has 2 parts because, like, yes, you want to know what your program is doing, you want to specify if you want it to be just in or out or undirected. The other piece is how we interpret that, kind of compared against a more objective reality. So what do we do with the kid who says they have 11 friends and their friends say, no, you don't, you got 3? Right? So, like, to me, that's informative social information, right? And if I'm thinking about adolescents and their things like their self-esteem and their perceptions of social support, that might matter a lot. So how we interpret that as being kind of inflated or not, I think is a more conceptual question. Any other questions? Okay. So again, some of the most interesting pieces of these centrality measures might be where we have very low correlations between them. So for example, a node with a high degree but low closeness is embedded in a very dense cluster of the network that is far from everything else. Right? Or an individual with a high betweenness and low degree is kind of like the example we saw before. So they don't have very many ties, but what ties they have are very important for network flow and for bridging other people. So you can think about how these kind of concepts are working together, and if you're measuring them together, what that could tell you about individual nodes. So there's another subset of centrality measures which didn't necessarily come out of the kind of big 3 that are mentioned in Freeman's 1979 paper, but one that is quite common, and I think there's a lot of concepts that relate to this, is Bonacich power centrality. Sometimes you'll see it called just Bonacich centrality or prestige or think I've seen it as proximity, prestige, or status. It's networked, so there can be like 7 different names for the same thing. But it's the idea that it doesn't just matter how you're tied to people, but it's who you're tied to. So you are more popular if you're connected to more popular other people. Right? So our classic high school example, if we're going to take the breakfast club tactic, is, are you king of the jocks or king of the nerds? Right? And those might be very different students. So that we're going to take into account the popularity of the nodes you're connected to. What's interesting about Bonacich centrality is that it has a tuning parameter that we can kind of mess with to get to different ideas. So here, A is just scaling, again, by the size of the network, but beta is a tuning parameter that you can change the settings for to make Bonacich kind of mean something different that might be of interest to you. So if it's set to 0, it's saying that we're only taking into account local structure. We're giving no weight to the ties of our ties of ties, and it essentially becomes degree. If we set it to 1, then we're giving more weight to that global structure. We're kind of interested in the ties of ties farther out in our network. So you can kind of adjust the scale of what Bonacich centrality is paying attention to in your network. You could also make it negative, in which case it's saying that so a positive value is saying you are kind of you have higher power or higher prestige if you're connected to other individuals with high power or high prestige. So you are more popular among more popular people. But we could make it negative and say that, in fact, you have a higher Bonacich power when you're connected to people who are relatively unconnected. And that might be very important for your process, because that might be an individual who can reach a part of the network that nobody else is really reaching, right? Or you might imagine that somebody who's very popular among people who are very unpopular might have a lot of power in some sense. So it's kind of interesting because you can tinker with it in that way. A paper that uses this comes from Stephen Haas and co-authors, and they find that adolescents with worse health have lower Bonacich centrality. And I think that's interesting to think about because so often we are fixated on the opposite direction of that relationship. We're thinking about how our network position affects our health in some sense. But of course, most of the time, especially when you're only being descriptive, your health is also affecting your network, right? So in their example, adolescents who are rating themselves as having worse health are also having lower Bonacich centrality. So they're less likely to be popular among the popular kids in their high school. So we could visualize this with a couple different beta parameters. So here I set beta to 0.5 and a negative 0.5, just kind of as an example. So you could see individuals who are connected to relatively well-connected others, and individuals who are connected to less well-connected others. And both of those would be high on Bonacich centrality. Eigenvector centrality is another one that is very common in the literature. You might have seen that in some studies. It's the same idea as Bonacich, except it doesn't have that beta parameter. So you can't mess with it kind of under the hood to make it mean something slightly different. So it's just saying that you are more important or more well-connected if the people you are connected to are also well-connected. But eigenvector centrality only works with symmetric or undirected data. Note that conceptually, it only works with undirected data. If you make R do it, it'll do it. It'll calculate your eigenvector centrality on directed data, but that's not technically correct, right? That's not conceptually accurate for how that's being calculated based on the underlying math. PageRank is another popular example because this is the Google algorithm. This is how a Google search is returning your wonderful Google search results. So that is using directed data. It's the same thing as eigenvector centrality using directed data. So again, like Bonacich centrality, but without that tuning parameter. So I think as PageRank becomes more and more popular from the Google's proliferation of Google and from the computer science standpoint, you start to see this more in health work. And Google also has a nice example for the layman about what PageRank is doing if you want to go back and read that later. But the important point is that it's saying websites that are very popular, that link to a website count for more than the links from unpopular websites. Of course, there are many, many more centrality measures that I'm not going to go through in an exhaustive laundry list for the next hour, but just some to put on your radar. So there's a lot of measures specifically thinking about peer influence or diffusion of norms and diffusion of innovations. A lot of them come from Noah Friedkin and his co-authors, looking at different different types of eigenvector centrality measures, of thinking about network autocorrelation. There's a whole class of measures called fragmentation centrality or key player measures that say nodes are central if taking them out of a network breaks up the network, fragments the network. Same with removal centrality. So looking at the effect on the network when you take a node out. Sometimes you might see these called induced centrality measures because we're really measuring the importance of one node by taking them out and seeing what would happen if they were gone. So it's kind of a tricky backwards way of thinking about centrality, but that's the way that there's a whole class of measures assessing the importance of nodes in a network. And you can imagine how that might be, really useful if you're looking at some kind of contagion process. Often you will see people using multiple measures in an analysis. And again, I think that sometimes that's the most informative indication of nodes' different positions when you look at things, how the correlations of these measures are working together. So one example is from Susan Ennett and her co-authors, and they test a whole battery of these network centrality measures against substance use. And they find that quite a few of them are associated with higher alcohol use for 15-year-olds. But you have to think about multicollinearity, right? So a lot of these are very closely related. In degree and Bonacich centrality, for example, are typically very, very well related if you have the positive and high beta parameter. So you need to be theory driven, I think is the best answer. You cannot just chuck every old centrality measure in your average regression or in your ergom and think it's going to turn out well. One, because you will be, waiting into your old age until your ergom converges, but also because you're going to have multicollinearity problems with your estimation. So it's better to be choosy based on your theory. Any questions about centrality measures? Okay, so we're going to move from thinking about the centrality of a particular node to how we could describe an entire network in terms of that characteristic. So what is the distribution of that power like in the network, or the distribution of popularity in our network? Because that might tell us something about the network overall, about the setting and the structure of this network that we might be interested in. So one of the most common ways of doing this, and probably one of the most important when you get into different kinds of statistical inference with networks, is thinking about the degree distribution. So that's just counting up how many nodes have what degree. So it's the frequency distribution of the degree that we calculated on our actors. So a simple random graph would have a Poisson distribution for the degree distribution. So any deviation from that suggests a non-random process. So if we count up the degree distribution for our toy network here, we see something like this, right? So we've got a lot of actors with just a few ties, and then we've got this long tail because there's only a few people who are really popular. Or if we do the degree distribution of another network, you typically see something like this, right? Remember, we had artificially cut out the isolates. So this is what you see. There's usually a few isolates, a lot of people who are a little bit popular, a little bit connected, and then a few people who are really connected. So that's kind of the typical social network degree distribution, something like a gamma or a power law distribution. So that's telling us that there is some kind of social process that's generating ties between nodes besides just randomness. Because if it was totally random, we'd have that Poisson graph for our degree distribution. And so this can become really important when you're trying to think about scaling networks, or if you're thinking about simulating something with networks. So this is from the classic work by Morris and Kretschmar in 1995, where there was kind of this panic about HIV networks, and the idea that all it takes is a few really connected hubs, and HIV is just going to explode in this epidemic of extreme proportions like we've never seen before, right? And they were saying, well, actually, most people are not hubs. Most people are monogamous. Most people have very few partners. And so if we take into account our networks, if we're simulating things about HIV in a network, we need to take into account that most people do not have a lot of partners. So they account for the degree distribution in their simulations, and in fact, they find much less of this kind of epidemic potential if you hadn't taken that into account. And so that degree distribution is going to end up being an element that you think about a lot if you're doing further simulations, like you'll see on, I think, Thursday. Of course, we can extend centrality measures besides degree. when we're thinking about the entire network. So Freeman centralization is looking at how centrality is concentrated or dispersed in the network. One of the most popular measures that you'll see is density. So density is looking at the volume of ties in a network, so what ties exist out of all the ties that could possibly exist. Our density is pretty low in our toy network, and that's fairly typical because most kids are not friends with everyone. Beyond that, we only gave them 10 spaces on the survey. So even if they think they are friends with everyone, they couldn't tell us so. So a lot of your density is going to be constrained by your instrument and how you're assessing your network or eliciting the ties between nodes. But we typically see lower densities for social networks and social relationships. Density can also be used in conjunction with other centrality measures. So we might think of interactions between individual node centrality and centralization or features of the entire network. So a paper from Guan and Camo looks at friends' depression and the contagion of friends' depression in schools of different densities in ad health. So in a high density school, friends with more depressive symptoms have a greater impact on individuals' depression than in low density schools. And that kind of makes intuitive sense, right? That if you're in a place that's very tight-knit, the symptoms of other people might have a greater impact on your own mental health. So beyond centrality, beyond just thinking about what is the centralization of a particular centrality measure, and we'll get into this a little bit in the lab. I didn't get into it too much here, but you could really take centralization of any centrality measure you want. We could think about the centralization of betweenness or of closeness. You know, we're just talking about degree and density here, but we can calculate centralization, some kind of graph level feature of any node level centrality characteristic that you would like. But we might want to think about it in tandem with attributes too, that it matters based on other features of nodes. In particular, you might want to think about homophily. So if homophily is the tendency of actors with similar attributes to be more connected, we can think about that on the level of the graph as well, and we would call that assortativity then. So you might have graphs that are more or less assortative, which means there's more kind of clumpiness of actors with a particular similar attribute, more or less homophily around different attributes. So this could be around individual attributes like gender or belonging to the same firm. So for example, we see much more gender assortativity in 6th grade friendship networks than we do in 12th grade, because in 6th grade, boys and girls think they have cooties, right? So there's much more gender assortativity. But you could also see assortativity based on structural attributes. So we often see degree assortativity in friendship networks because popular kids want to be friends with other popular kids, not the unpopular kids. So the structural information is something that can provide an attribute that people are sorting on as well. You also could expect disassortative mixing in particular cases. Like for example, if you're measuring heterosexual relationships, you're gonna see a lot of gender dissortativity in your network because you're expecting kind of that anti-mixing on the attribute. I wanna note again, like everything else in this lecture, this is purely descriptive. So we're not saying that this is any process of influence or peer influence. In fact, we know it's very likely selection, right? So for example, that boys and girls are choosing to be friends with other boys and girls. They're obviously not changing each other's gender, right? So we're not trying to distinguish things like selection or influence, but from a descriptive point, describing things like the assortativity on different characteristics or structural features could be really informative. So we see a lot of assortativity in our network that would indicate some kind of person-level homophily. So I think here, let's see, green is 7th grade and blue is 8th grade. So we see some separation by different grades in our network, but not too bad, some assortative mixing. And then triangles were male respondents and squares were female respondents. So we see quite a bit of the gender assortativity or the cootie effect, if you like. Okay, there's a whole other suite of popular centrality measures that are really focused on different mechanisms for how this is coming about. And a lot of these come from the kind of business side of the social networks literature from Ron Burt in 1992. And he coins the term structural holes, which is thinking about the absence of ties between alters. So that's kind of tricky because you're defining something by what it's not. But the idea is that there's something important about nodes who are connecting people who otherwise would not be connected. So that you might have particular power or social capital, you might be able to negotiate, you might be able to innovate, right? A lot of this, again, is coming out of the business world, so it tends to focus on those topics. There's very little health literature that is explicitly talking about structural holes. Part of that might just be differences in terminology. Part of that might be just the tradition of where the concept has originated. There's some of it out there, especially from Ben Cornwell with ego networks, thinking about structural holes. But this includes the idea that redundancy introduces constraint, that alters who are tied to each other might have more power over ego's actions than if they weren't tied to each other. So they might have more power to regulate your behavior or limit your ability to negotiate if they are tied with each other or communicating with each other than if you're the only person connecting them. So it's the idea of where ties aren't a structural hole that could be really meaningful. And so we might get some kind of power from controlling info. We might get some kind of brokerage, again, innovation, if you are bridging a structural hole. And this will go all the way back to Georg Simmel's theory of sociology and triads in the early 1900s, what he calls the tertius gaudens, that there's the third person benefits if it can make two other people fight with each other or negotiate or compete in some way. And so you might see a kind of subset of features that would go into calculating things like brokerage or power or structural holes in this perspective. I'm not going to get too in-depth here, but I think they're important to be aware of, and I think that this is an area that's ripe for being ported into the health literature. So we could think about the connections between others as introducing kind of a kind of efficiency or constraint in our network. And there's also a lot of measures with hierarchy that are specific to BERT. One thing that's tricky, again, is in networks, we're often using very different words for the same thing, and sometimes we're using the same words for very different things. So you want to make sure that hierarchy, if you're using it in the sense of kind of structural holes in brokerage, really is measuring this BERT style of hierarchy. So the extent to which constraint is concentrated in one actor. Okay, so now we're going to transition to centrality and two-mode networks. Before I do that, are there any questions, any ideas, anything anybody would like to bring up for the good of the cause here? Sure.
What if your nodes are teams, people who belong to?
Yep, so this definitely works in teams. This would definitely apply to teams conceptually. I think the interpretation would be different. So if you're, if nodes are individuals and the setting is a team, I think that's almost exactly what this is written for, and you will find a lot of literature that's supporting that. If your nodes are teams and the edges are connections between teams, it would still be measured in the same way. The interpretation would be different. Okay. Good question. Yeah.
So can you tell a bit more about the relationship between the bridging structural holes and also eigenvectors? Because the eigenvectors. And
yeah, so they're very similar. So the question was, why would we talk about bridging structural holes and talk about eigenvectors? Shouldn't they be kind of the same thing? So, well, bridging structural holes is talking about making a link that otherwise wouldn't exist, right? Eigenvector is talking about you are more popular if the people you are connected to are themselves popular, right? So one is kind of aggregating up your connections, their connections, things like that to take that into account if we're generating a measure of power. So a higher value means you're connected to other people with high values, right? Structural holes means specifically that you're bridging other individuals. It's not really taking into account who they're connected to, if they're popular, et cetera. It's saying that there's something at a more micro level if you are bridging a gap that otherwise would not be bridged, right? That's the point of the structural hole. I feel like it's always hard to say because you're kind of talking backwards about what wouldn't exist if you weren't there. But so if anything, I think that structural holes are closer to the idea of betweenness, that betweenness value for an actor is how often they're on the shortest path between other individuals, right? So they're very similar, but the betweenness is just operating along the idea of the geodesic and individuals that could be connected through multiple steps, so the multiple paths, right? And the structural hole is thinking at the micro level of, are you connecting something that, bridging in a sense that if you weren't there, you would not be connected. So I might be on the geodesic between Jim and Leanne if we plot the social network, but there might be 4 other ways that they are connected to, okay, for example. So they're not incompatible, right? But they're not the exact same thing either. I think it's just that there's different network traditions that have kind of named things differently and measured things differently, and so we have a lot of similar concepts that aren't necessarily contradictory or exactly the same thing. Okay. Does that help? All right, if you have more questions, I'm happy to talk after, too, if there's a specific case to discuss. Anything else? All right, let's talk about two-mode data. So what would centrality look like if we were in a two-mode network? So as a refresher from what Jim was talking about Monday afternoon, two-mode network data is most often bipartite network data. Sometimes you might see it called affiliation network data, and that refers to networks where you really have two different types of nodes that can be connected to each other across the set, but not within the set. So we have between set ties and no within set ties, and that's much harder to describe than it is to understand, I promise. So this is the data set that Jim was using. It's the Davis Southern Women data set. So it was collected in the 1930s of women. I think it's Mississippi, but you said Charleston, so maybe somewhere in the South. That's all we know. We call it the Southern Women data set. It's from their book, The Deep South, where they do an in-depth ethnography about race in the South. But they looked at newspapers and did interviews with people and looked at 14 different social events and the women that attended them. And so we have connections between women who attended events. Events can't be connected to events, right? And women can't attend other women. So you can only have connections between women and events in how we've defined what a tie means in this set. The theory for this, a lot of it harkens back to Brager's work on the duality of persons and groups. That's kind of the canonical citation you will see anyone throw out in their first paragraph of their sociology paper. That's with two-mode networks. And that's the conceptual idea that individuals are shaping groups, right? So individuals who go to a certain event shape the social structure of that event. Individuals who join a club or are on a team, they're defining the group, because the group's made up of individuals, but the structure of the group is going to define individuals as well. So the structure of the group is going to shape interactions. You can only interact with people at a party who are at that party. So there's a constraint placed by the group on individuals, and there's kind of this constant coevolution at this conceptual level between individuals and the groups they make up, and how the groups are conditioning individuality as well. Okay, so two-mode network data, it's kind of hard to clearly quantify features of this two-mode network data when you've got individuals who are connected to events, but they can't be connected. Individuals aren't connected to each other, events aren't connected to each other. There are some kind of properties and measures out there for dealing with bipartite network data when it's bipartite. Most of the time, people do what is called a one-mode projection. So they take this two-mode network data and force it to be one-mode network data. So this is when we take the joint connection through the opposite set of nodes to become connecting edges, which again is harder to define than it is to just describe. So if we've got our network here of women who attended events, and we're going to do some, in the old school by hand days, do some fancy matrix multiplication and project women who share a tie if they were at the same event. So from this information, we say, okay, if Olivia and Myrna were both at event number 11, make a tie between them. And in fact, we see a tie between Olivia and Myrna. Right, so the one-mode projection takes the information from whatever we're getting rid of. If we're just going to project the connections between women, we're going to take information from events and make that the ties. You can have the same projection of events connected to events, and we'll look at that in the lab too. How do we go from this two-mode network data to the one-mode projection of women to the one-mode projection of events? Right, but you can go either way. Note that there's a few properties of these graphs. So for example, you can't have directed network data because it's co-attendance, right? And that gets back to what Jim was talking about, that if the tie is co-attendance, you both have to be there to have been co-attendant. So it's either an existing tie or no tie. There's no directed discrepancy. So another example comes from that Landon paper that I was saying, just had great visuals for the medical community of non-networks. So they look at physicians and patients. So you could have a patient that's seeing 2 different doctors, and of course, doctors are seeing more than one patient. And so they take this bipartite data and project it to look at physicians who are connected because they share a patient. So for example, physicians 5 and 1 are both seeing patient A. So you get to the one mode projection, and the ties here, the edges are representing shared patients. And you would have the same projection the other way. We could look at patients who are sharing physicians if we wanted to, for some reason. And that article, they're using, I think, over 4 million Medicare records to look at these physician and patient networks, and they actually look at differences in centrality in the one-mode projections based on geographic distances in the US. So they look at things like clustering, I think differences in betweenness of different kinds of physicians. So primary care physicians were much more central in, I think, in rural networks, for example. So that's another one to look up if you're interested in that process. But there are some concerns with centrality and one-mode projections of these 2-mode network data. I think how important those concerns are might depend from the network scientist who is expressing their viewpoint on it. So some of the idea, some scholars would say, in fact, the bias is so bad, we shouldn't even be doing this at all. Like, we shouldn't even worry about centrality and one-mode projections because it's all completely biased. So projection itself is going to inflate edges. And projection itself is going to create, because it's inflating edges and creating clumps around shared patients or attending the same event, it has a tendency towards cliques. And that tendency towards cliques is leading to things like higher density measures, higher clustering coefficients, higher betweenness, right? And that isn't because of that's of interest in the network, that's inherent to the fact that we've done this one-mode projection of 2-mode network data. Not to mention, what would it even mean? Right? What would something like high betweenness of women attending events mean? Like, maybe you can come up with an idea for that, like that there is something meaningful in that interpretation, but the interpretation is perhaps less obvious than if we didn't have projected data. There's been some solutions to this. So perhaps one of the wisest solutions is that because these numbers get artificially inflated during projection, don't get obsessed with the actual number. You can't get excited about saying, oh, look, my clustering coefficient is 0.4. Wow, a whole 0.4, amazing. Because that's just an artifact of the projection. Instead, you have to look at things like the order. So are there women who have much higher betweenness in our Southern women data set than other women? So things like the relative values instead of the actual absolute values of those numbers, because we know that there's just this inherent bias from the mathematical fact of projection. There is a lot more information on this about how dire these issues are of bias in one-mode projections, of what we should be doing to solve them. There's entire suites of R packages that are designed to combat this bias and to work with them in a more thoughtful way. So I've given you a lot of sources to check out, and we'll come back around to some of those in lab too, so you could see it. But I think the most important thing is that to be aware that this exists if you are working with this kind of data, and to be very thoughtful about your interpretation and about how you were thinking about those measures, particularly in non-absolute terms. Any questions with this? Okay, I've got one more bipartite example, then we're gonna head back to one-mode land. So this is from work by Petty and co-authors, and they're looking at administrative data from the VA, and they look at veterans who have visited physicians, and then they look at the coincidence of different medical codes for those visits in predicting homelessness. So they've got veterans. I apologize for the graininess too. There's only so much I could blow up the images from other people's papers. So veterans had visits to the doctor that are coded according to the type of the visit. So they aggregate that so that there's all the different codes within a certain period of time that they analyze in their records for a veteran. And then they project that bipartite data into one-mode data by saying these are the codes that co-occur. So we can see the associations of why people are going to the doctor, essentially. And they can look at comorbid diagnoses, or the comorbidity of the medical codes in those visits. So of course, as you might expect, PTSD and depression were often together in different kinds of visits. What's interesting is they extend this and say, like, okay, so of course we can see which visits, which types of visits are associated with each other, which different types of medical codes are related to each other, but they can also track over time how visits move from assessing routine ailments routine physical ailments to adding in alcoholic dependency and how that increase in connection to alcohol dependency in the medical code predicted subsequent homelessness. So I think that that's a great example of somebody who's using two-mode network data, projecting it into the one-mode network data, and being very thoughtful about how to use it in a meaningful way that has a clear interpretation. Okay, we're about to leave centrality behind. Any questions? Do you want to take like a 2-minute stretch break, or you want to power through? I see nods. 2 minutes. All right, so centrality measures, for all their complicated, many 200 different ways we could define them mathematically and talk about them and name them, they're pretty standard in the idea of it's some way of defining the importance of an individual node based on the underlying graph theory. It gets a little more interesting and exciting, I think, if we move into thinking about connectivity and cohesion, where we're not just talking about an attribute of a node, but the features of what makes this entire graph connected or cohesive and how we might think of things flowing through our network. So we could think of this as what are the structural arrangements or characteristics of networks underlying this actor's centrality or importance or power? What are the structures that might be leading to this? So on the most local level, we have the dyad. So we might want to know about the dyads in our network overall. A lot of times you would see the dyad census called the man census. That's not, inherently, intentionally gender biased. It's just talking about mutual, asymmetric, and null ties. So if we have directed network data, we could have mutual or asymmetric ties, or we have a lot of nodes in our network who aren't connected to each other at all, and they'd be a null dyad. So we could measure the proportion of our symmetric dyads from all of the dyads or of the non-null dyads. So out of the symmetric or asymmetric dyads, how many are symmetric? Out of all the friendships that exist, how many of them were mutually agreed upon in our data? So the dyad, of course, is the most local little unit of network structure, the most local relation we have in our network. We also have triads, and this becomes the U-man census. So I'm talking about the uniform random graph of mutual, asymmetric, and null ties. This is the complete census in directed network data of every triad that could theoretically exist. And each number here stands for the position in the MAN census. So this triad has 0 mutual ties, 0 asymmetric ties, and 3 null ties. It's 3 people who aren't connected to each other. Right? This dyad over here has 2 mutual ties, 1 asymmetric tie, and 0 null ties, etc. When you have ties that would have the same count, so here, for example, we have different triad shapes that have 0 mutual ties, 2 asymmetric ties, and 1 null tie. We add a letter to say it's the one that points down, or it's the one that points up. Right? It's very deep stuff. It's a cycle. And so we could take the triad census of our network. If you have a big network, you might want to think twice before you push that button because it could take a very long time, but you could do it. And this, I think triads are hugely of huge interest in sociology because, back to Zimmel and Holland and Leinhardt, people get really excited about triads because that's when the interesting social stuff starts to happen. As soon as there's a third person you could blame something on, right, it gets much more exciting in terms of power and negotiation. So we can characterize these non-random patterns in the triad census, and we know that something social is happening if we take the triad census. We can count up the triads of possible type. We might be particularly interested in the transitivity of triads. And so transitivity is for every triad where if I is connected to J and J is connected to K, then I is also connected to K. The idea that a friend of a friend is a friend, right? Or back to Granovetter's forbidden triad, that it's very unlikely if I knows J and J knows K that I doesn't know K also. Oh, and here we have the illustration. So if I knows J and J knows K, probably I knows K too. With directed ties in particular, we could further categorize transitivity as our triads as transitive, intransitive, or vacuous. And so we could do that to our triad census. We could say, okay, here are all the possible types of triads you can have in directed census or directed data, and here are the transitive ones, here are the intransitive ones, here are a few that are mixed. And vacuous would be where we don't have the ties. So we're not saying that have people who don't know each other are intransitive in the same way as other intransitive arrangements. we can extend this to a network level by comparing the triad census we observe in our network to what we would expect by chance. And a lot of times we'll see very different patterns in, say, a tendency towards transitivity in a social network, or a tendency against cycles. It's very rare in a friendship network that A says they are friends with B says they're friends with C says they're friends with A, and nobody agrees, right? It's just one big cycle of everyone pointing at everyone else. We often measure the clustering coefficient based on transitivity, so that's the ratio of closed triads over total triads. So how often, when I knows J and J knows K, does I say they know K, or do we see directed friendships in that direction? One great example using this comes from Ashton Verdery and his co-authors, and they're looking at respondent-driven sampling networks of individuals who are injecting drugs in the Philippines, and they're comparing two networks in two separate cities. They see the city with the much higher clustering coefficient based on transitivity also experiences a much higher and faster spread of HIV and AIDS. So there's something about that network structure induced by higher transitivity that is leading to perhaps higher disease spread. And if we think about the relations of our ties, or the positive and negative features that we could have of different relations as a characteristic of edges, we can also add social balance to the equation. And I think Greg was talking about this a little bit earlier. The idea that we assume that the friend of my friend's friend is my friend. But we can extend this if we are talking about negative ties as well. So if I'm friends with person B and person B is friends with person C, chances are I'll be friends with person C, right? And that's kind of transitivity like we just talked about. But if person B really hates person C, it might be kind of awkward if I'm their friend. And in fact, we might see a tendency towards balance, that the people that my friends hate, I also hate, okay, or dislike if you want to be polite. Or the people that I dislike or I don't get along with or that bully me in school, right? Their friends, I'm also probably not going to get along with. I'm going to preserve that social balance. It gets a little bit weirder when you think about the last one, my enemy's enemy is my friend. But I think we've all had an experience over bonding over some shared dislike of something or someone with another person, so you can imagine that one working out as well. So the point being that we can take this information about different types of edges, right, or different features of relationships and extend it to kind of these social predictions, because as social animals, we like to preserve social balance. So in our toy network, if we take the dyad man census, we see we'd have 22 mutual connections and 67 asymmetric connections. If we count up all of our little triads, we could get values for each of those as well. You would notice that we don't have a lot of these kind of asymmetric cycles like I was talking about. And we have maybe just a few that are completely mutual in our network. In the lab, we're going to talk about how you would compare that to what you would expect by chance. We've got 141 transitive triads, and our clustering coefficient would be about 0.36. So if those are the kind of local components as dyads and triads, how can we describe the connectivity or cohesion of a network overall? There's a couple of ways that people historically in the social networks literature have described the connectivity of a network by kind of naming different types of networks. One of those is a scale-free network. They call it scale-free because their argument is no matter the size or scale of the network, you're going to see this kind of pattern. And features of a scale-free network is that locally, there's a few high-degree nodes who are acting as hubs. There are a few really popular people, say. And we might expect some kind of process that drives that, like preferential attachment. So popular people might become more popular because they are popular, right? On a social media effect, somebody who gets a couple thousand Instagram followers is going to pop up in everybody else's feed and suddenly have thousands more Instagram followers or something like that. There's something about popularity that's going to drive increased popularity. And that local pattern leads to a global pattern of networks with a highly skewed degree distribution. So like we were talking about before, you've got a few semi-popular nodes, and then you've got a lot of semi-popular nodes and a few really popular nodes that are acting as hubs because of preferential attachment. And this might have huge implications for disease diffusion. When we were talking about that 1990s HIV and AIDS panic, a lot of that was focused on the idea of scale-free networks, that a few high-degree hubs could really drive the potential for diffusion because of the scale-free nature of a global network. Most of the time, in social networks, we don't observe a pure scale-free nature to the network. There are a lot of other social features that get in the way, like reciprocity and transitivity, or prohibitions against force cycles, or scheduling and timing, that it's tiring to have friends and you can't have as many friends as humanly possible, right? Or something like that. So it's rare that we see a pure scale-free network in social networks in the wild, as it were. Instead, we might think about kind of a counterpart classic type of network as a small world network or a small world phenomenon. And this is thinking about what is the probability overall that two nodes are connected. Small world graphs are typically large, rather sparse, but very highly clustered. Watts, who does most of the seminal research on this, calls it the caveman world, that you've got these dense clusters that aren't very connected to each other. If we think about that from a graph theory perspective, that would be graphs that have a relatively small average path length and large clusters. But one feature of small world networks is that it doesn't take much local change to have huge effects on the global network structure. So for example, one or two shortcuts can have a huge impact on the connectivity of the graph and then say the diffusion potential. So there are features of these different kind of typologies of networks that you might come across in the networks literature. So how can we measure something like the small worldliness of a graph or other cohesive characteristics of a graph? So again, the clustering coefficient, we already talked about that as measured as a feature of transitivity. Sometimes you'll see that measured as ego network density, so average local density, trying to assess that clusteriness. Another measure, kind of a more complex way of thinking about cohesion, is structural cohesion in the graph. So to what extent are networks and subgroups within that network sticky or cohesive and resistant to disruption? How we could describe cohesiveness by how hard it is to break apart our network. This can be really hard to measure. And it can also be kind of, I think, conceptually difficult to think about what are the theoretical components that would lead to cohesion or the stickiness among the graph or subgroups of graph. So we could think about how much the connectedness of the graph relies on just a few nodes in our network. So the more paths that are linking up the network through more nodes, the more cohesive it might be, if it doesn't just depend on one or two actors connecting everything in the network. And so to get to that, we would assess reachability. The idea that actors are reachable if there is some path in the network that would connect them. So reachability as a feature of your overall graph, not to be confused with the reach of a particular node, but overall reachability. And note that this is about the pattern of ties in the network. You can't just look at the number of ties, and you can't just look at density. So in these two little examples, they have the exact same number of edges and nodes, the exact same density, but simply changing the position of one node drastically changes the reachability and the structural cohesion of the toy graph. So again, we could have the same volume of ties in 4 different examples here, but they have very different cohesiveness in the network. So by the time, if we move across from this network with 2 distinct components to network 3 here on the end, there would be 3 separate paths that could connect individuals in the network. And so we might think that that might be more cohesive and resistant to disruption. So to measure that, we might want to be able to assess components. So how many pieces are there in the network, essentially? A maximally connected subgraph where there's a path between every node. Sometimes we talk about strong and weak components. Strong just means you're taking into account directionality. Weak means it does not, that you're just assuming it's undirected. We can refer to a cut point as a node whose removal would disconnect the graph, make different components. And so then we could call the cut set all the nodes that are cut points. So we could refer to the cut set as the groups of nodes, the groups of cut points in our graph. And so if we take these ideas together, we can get this kind of description of structural cohesion as the minimum number of actors who would disconnect the group if they were removed. Or if we're thinking about it in terms of edges, the minimum number of independent paths that would link actors in the group. So we can assess the cut points in our toy example. This is the point every year where I have to confess that I made the mistake of not setting the seed in my R graph. So if you notice, the graph is like completely rotated and moved around a little bit. That's my fault. So it might look, it's the same people as before. It's just looks a little different because I didn't set the seed like you will all be taught to in lab, so you don't make this mistake. So if you're looking at it and you're like, that's not how it looked before, you're correct. And that's why, but it's still right. So don't worry. So we see that some cut points are just connecting, what you might call pendants in the graph. Sometimes they call them pendants because they're just kind of dangling off the edge here. But we've got some other cut points as well. And so thinking about that cut set of networks whose removal would really break apart the graph, those are kind of indicating the importance of those nodes in maintaining the cohesiveness of the graph. There are a lot of different ways that you can define components. So you will see K components, excuse me, where K is referring to the number of paths that has to link the different nodes. So very often we talk about bi-components, and that means everybody is connected by at least 2 independent paths. We can say, because of that definition, we can see that every member would have at least K ties, so you can only be connected by 2 paths if you have at least 2 ties. But 2 different K components can only be connected or can only overlap by K minus 1. So if we're talking about a network with 2 separate bi-components, if they can have 1 member that overlaps because they're only connected by 1 independent path, but if they were connected by 2 independent paths, then we wouldn't have 2 bi-components. It would be 1 big bi-component because everybody would be connected by 2 paths. So you could think about the formal definition if you had to define these groups. They're also nested within each other. So we could think about this as what Jim terms embeddedness in his work in Moody and White 2003, so that we can identify different groups in the network and then remove K cut sets to identify these more deeply nested groups in the network. So if we look at person number 7 here, they're part of this densely connected group, which is nested in this larger group with the dotted line, which is less nested in the entire overall component that we're visualizing here. But the idea being that if you look at cut sets, you can get these like kind of successively more deeply nested or embedded components in the group, or really people in the network. Sometimes we talk about cliques. So this is another type of substructure. These are all basically just different definitions for how we might define a group or want to look at different groups in our network, or important kind of substructures in our network. So a clique is where all members are connected to each other. That is pretty strict. It's very rare in a friendship network that you would have a group where everybody is connected to absolutely everybody in that network. So we might want to relax it and consider who's connected by 2 steps or by 3 steps, and that would be a 2 clique or a 3 clique. You could also think about it as people who are connected to at least that many others in the group, regardless of the connections to everybody but themselves of a clique. So this gets kind of further relaxed from clique to a plex. So you could have a 2-plex if you wanted to further relax that. These can be very hard to calculate in large networks, right? And very hard to kind of derive useful meaning from if you have calculated it and there's not like one clear giant clique in the network. So I think that as network analysis is expanding, it's rare that you see as much about cliques and plexes and clans and et cetera. A clan is the same type of thing, but it's looking at, it's another way of relaxing the definition of a clique, that you're connected by a distance of paths, of 1 path or 2 paths, however many you set, but only through other members in the group. So again, it's just defining groups, but instead of saying you have to be, a group only exists if you are connected to everyone else in the group, it's a different kind of set of connections and relaxation. More often you will see a K-core, and that is defined as a group where members are joined to at least K other members in that group, even if not everybody is connected to everyone else. So if we have a 2-core, it means that people are joined, that's everybody who's joined to at least 2 others in that group. So in our toy example here, we've got the, everybody is connected at least once, because we chopped out all our isolates, so they're in green. People who are connected at least twice to others in the group are in blue. People who are connected at least 3 times to others who are connected 3 times are in the navy blue. So we could visualize just the 3 core of our network. That's the group that's connected at least 3 times to others who are connected at least 3 times. So that's centrality and then connectivity and cohesion. We're going to talk very briefly about structural equivalence to give you some intuition of the idea behind different types of equivalence in terms of roles, and then we'll move on to the lab section. So you've gotten the overview now from Jim and from Craig about thinking about networks as pipes that things are flowing through and thinking about networks as positions. And kind of the extreme of thinking about networks as positions is thinking how we can abstract networks overall to sets of roles or positions. So Jim gave you the example on Monday of a nuclear family, where we might expect, romantic love between these partners. We might expect care and nurturing in these ties, and we might expect bickering between these individuals down here. And the individual node doesn't really matter if we're focusing on the structure of that network and those types of relationships. So we can abstract away from individual people and say, this is what a family looks like, or this is what a nuclear family might have relations like. So we can describe subsets of actors and nodes that have similar structured relations. We might have a nuclear family over here on the left, and then on the right, we could say that's something like a boss, a middle manager, and employees at a company. And we might expect to see that structure at a lot of different companies, regardless of who's filling the particular role. So structural equivalence formally is actors who have the same ties to the exact same people in the same network. That's very rare, where everyone might have the exact same patterns of ties, and that might be more restrictive than we're actually interested in when we're thinking about roles. We don't care if you have the exact same people in your family. We want to know who's in a particular role in this family, or we don't care who your employees are. We want to know if you're a boss in our corporate network. So we relax this to regular equivalence. Actors are equivalent if they have ties to the same types of alters, even if they're not necessarily the same exact alters. So if you have ties to other alters with the same patterns of ties as someone else has, that would make you regularly equivalent. I'll give a warning that sometimes in the literature you will see these used kind of like loosey-goosey or interchangeably, so people will be saying structural equivalence and they're really measuring regular equivalence. So I wanted to give you the formal definition, but that might not always be strictly followed, per se. So for example, in our little fake corporate network here, actors C and D and actors E and F are formally structurally equivalent because they have the exact same ties to the exact same people. C and D are connected to A, and they're connected to G through J. G through J, that group is also structurally equivalent. K through N is also structurally equivalent. They've got the exact same ties to either C and D or E and F. But then we have regular equivalence between A and B because they're both connected to two people who are connected to each other and connected to four people below them. Right? So they're connected to the same types of structures, same types of alters with the same network profiles, even though they're completely different individuals. Yeah? So I think it depends on what you're measuring, right? So it depends on what our network is, what our setting is, what ties are. So one example I'll show in a second is work from, I think, Fujimoto and Valente. And they find that in adolescent friendship networks, individuals' regular equivalence profiles predict their smoking behavior better than their actual friends. So practically, we might say there's something about being maybe semi-popular and connected to many different groups that makes it really easy for me to get cigarettes. It makes me want to try to be cool by smoking them. And so I might be more likely to smoke, not because of the particular individuals I'm connected to, but because of those features of my position. So beyond that, I think beyond examples, it's hard to generalize in an interpretive way because it completely depends on the context of your network and setting. Okay? So that's a good question, is how do we get from something like this to something that might matter, right? So C through F would be regularly equivalent, even though they're not structurally equivalent, because they're both in the same type of structure, even though they're not connected to the exact same people. And G through N are also regularly equivalent. And so that gets us to block modeling, which I'm going to say from the start, we're only talking about a tiny little bit. We're getting a teaspoon into block modeling. So if you are interested in it and it sounds applicable to you, you can follow up on it. There is a whole deep, scary literature about this that you're welcome to look at on your own time. People get really into things about defining groups. And you're going to hear more of that tomorrow from Peter Muka, tomorrow or Friday, but or Thursday. I don't even know what day today is. But anyway, block modeling would be the process of identifying these similar positions in the network. So block comes from the idea that if we were doing this kind of the old school way with an adjacency matrix, we'd be looking at groups of similar actors in a little block in our network. So that's what the name comes from. But if we were to block model this network, we would get a graph of our block model that looks like this. There are 3 different positions based on regular equivalence, right? So position 1 is connected to itself. So you get this little self loop because A and B are connected. So nodes in that position are connected. Then they're also connected to individuals in position 2. Position 2 is connected to itself. There's individuals in position 2 who are connected to each other. And then they're connected to position 3. Position 3 does not have any connections between itself. G through N aren't connected to each other at any point. They're only connected to the people above them. So they only have connections to position 2. They don't have that self loop. Okay. And not to get hung up on the description of the graph here, but the point being that we can go from, all right, these individual nodes occupy a similar set of positions to actors with similar network profiles. And because of that, we can kind of make a role of individuals occupying a certain position, and we can look at relationships in the network of people between those roles. You could also, include attributes into this information if you wanted to think about that, so other characteristics of the network. And you could get kind of increasingly abstracted about this. So you could generate and think about kind of core and periphery structures of individuals who are, dense positions that are densely connected in the network versus more peripheral positions. This, I think, is largely untapped in the social networks and health literature. I had to work very hard to find one example of somebody using this in a paper. So if you have other examples, please let me know. So again, this was the example I was speaking about earlier in response to that question, but they have a paper that looks at substance use among students in a middle school or high school, I forget which now, and they find that being connected to the same types of peers in the same type of network positions and peers that have the same types of behaviors matters more than who you're actually connected to in terms of distinct individuals, and that those measures are better predictors of your substance use than our traditional measures of centrality or cohesion. So it's not just something like being popular, but it's being connected in the same way to other individuals with the certain profiles of behaviors and networks. Okay, so again, I know that's like half an ounce of the entire bottle of block modeling or structural equivalence, but does anyone have any questions? Okay. So just to wrap up our last whirlwind tour here, there are a lot of ways you could describe your networks. And there's a lot of ways to characterize which nodes might be particularly important or central within your networks. And a lot of this can be very meaningful to understanding what's going on in your network, to expressing the importance of your social network to your audience, even though we haven't even touched on things like causal inference or statistical inference in that way. So we've talked about individual node properties. We've talked about the entire network counterparts of those properties, so things like degree and degree centralization or degree distribution, so centrality. We've talked about structures and subgroups, connectivity and cohesion, so how we can go from these are important individuals to what makes my entire network cohesive or connected. And we've talked about how this can be abstracted into roles. Again, you could be framing this as a micro, meso, macro process if you're used to that way of thinking. So we are talking about features of individual nodes in terms of their network position, features of subgroups, or defining subgroups and subgraph structures and roles, and talking about features of the entire network. We can characterize our entire network based on its centralization or connectivity. A few things that we haven't even talked about here at all. Dynamics. So all of my examples have been static, cross-sectional. We haven't even talked about the idea that your ties are changing over time, right? Or the effects of these changes and things over time. So again, this is just kind of one little slice of the networks literature and typical questions you might have. There are many, many more two-mode network methods or two-mode specific issues out there that you might want to be aware of if that's the kind of data you're working with. And there are a lot more kind of challenges that have been slightly glossed over here in terms of things like defining communities and groups. So how do we define different groups in our network, and you'll get some of that again with Peter Muka. And there might be a lot of specific measures to your research question or in your subfield that are particularly used in that area that you might need to be aware of that we didn't talk about here. And so with that, I'll take your questions. Thank you.
Could you go to slide 31?
Tell me if I get there. 'Cause I don't know if it's exactly. Also, it is a grotesque amount of slides, but like half of them are hidden, so don't panic.
I think it's about the power centrality.
Yes. This guy.
Oh, it's the last.
Oh, this?
Yeah, this one,
Okay,
yeah.
thank you. Sorry.
So I wonder, because the beta, we can change the size of the beta, so how we will design the size of the beta to make sure we maybe taking more consideration of the local and all about more about the global. So could you give some examples of how we design?
Sure. So the question, just because I think the last part got caught on the microphone there, the question is, if you can change that beta parameter, how do you pick one? How do you know, is this fair? Like, how do you know how local to make it or how global to make it? What's the intuition? So I think that, so first of all, some network data sets come with it already calculated for you. So for example, in ad health, Bonacich power centrality is calculated and available in the network data set. And it, so if you're going to redo it and mess with it and do something different, you'd have to definitely note that in your structure or in your paper in describing your methods. So sometimes, just so you're aware, if you're getting somebody else's Bonacich power centrality, it might be calculated based on a particular value, which is generally available in the codebook. So in ad health, it says in the codebook how it's calculated. If you're doing it yourself, I don't think that there is any particular rhyme or reason within the bounds of it being kind of sensible, justifiable, and robust. So if you define it in a particular way and you realize like tweaking it one tiny little bit completely, destroys your results, then that's not something you want to hang your hat on, probably. I think that that's a criticism of the measure, that some people don't want to mess with Bonacich power centrality because it is something you can tune. But I think it's also a strength that if you are interested in people who have kind of power in like these decentralized groups, this is the way that you would measure that. So if I want to know individuals who are highly connected to other people who are not well connected, then making this beta parameter negative is the best way I could assess that. And it's like any other measure, if you use it well and sensibly and describe what you're doing, it's theoretically justifiable, I think it's fine. But if you don't tell anybody what you did, don't have any reason for doing it, it's not going to go over very well. Jim, do you have a better sense of the literature?
It's a bit of an art to pick the beta measure. There's a nice paper in the journal Social Structure, JOS Online, it's a free journal published by INSA, the Social Networks Organization. I'm just blanking on the author's name, but there's only like 4 or 5 papers a year in that journal, so it's relatively easy to find. Where he goes through and he does a bunch of computational experiments on different kinds of networks, different beta weights, and shows you how the effect, how to set it, and what the effect of it does. In most well-behaved networks, it'll behave essentially monotonically. So if you made it a little bit bigger, the effect will be a little bit stronger. Or it'll be a smooth transition. When it's not a smooth transition, it's usually because your network has really strong clustering. And so whenever you have one parameter size, it's essentially always capturing an influence within the cluster size. It'll give you one effect, and you jump out of the cluster size, and the effect changes. So if you see a discontinuity as you're changing beta, it's probably because there's an underlying modular structure to the network that you haven't accounted for. Now, if you're doing the exploratory work that we talked about before, you would have noticed that to start with. As soon as that, look, my network has really strong clusters, and you probably would have been analyzing 75 clusters anyway. And so, all that's to say, that would be a really slow and cumbersome way to find out your network has communities. But
the best rule of thumb is to make sure whatever measure you choose is theoretically justified or conceptually justified and robust. So you check it and make sure it doesn't go crazy if you make a small change. Does that make sense? Okay. Other questions? Yeah.
Will you be including a list of references with the presentation?
Yep. So the list of references is on there. It's the last 2 slides.
Okay, great. Thanks.
And if I missed something, my email is on here as well. And you can feel free to email me or if something isn't clear. But I think I have the whole shebang in very tiny type on the last 2 slides.
Tiny is fine, as long as it's there.
Great. Yeah.
I actually also have a question about references just because there's a lot, and this is all really new to me, but I'm particularly interested in this sort of parallel comparison with the micro, meso, macro, and then like individual and everything. Is there a good reference that you would recommend sort of talking about that? And yeah.
Yeah, so I would say off the bat, the best kind of starting point reference that is going to make this tangible, particularly for health questions, is the Valente Social Networks in Health reference. So that it's called Social Networks in Health by Tom Valente. That book.
It's in my
You know. Okay, there you go.
just like I haven't read it yet.
Yeah, that's fine. So I think that's the best starting point. I think that most of the references are looking at a specific subtopic within that. So it's papers that are empirically applying, density and looking at betweenness and at health or something like that. So that's the best general reference to my knowledge. The Wasserman and Faust is like the old school, here is how we calculate it according to graph theory. So that almost serves as a useful desk reference if you need to look something up. But beyond that, I think the one with the most interpretation would be social networks in health. Does anybody else have a favorite reference, particularly that would get at micro, meso, macro? I will say when I made that, I didn't have a reference in mind. I was just wanting to talk about it in that way because I think in sociology we do that a lot. We try to separate those things into those tiers. So I didn't have something particular in mind that really addresses that concept. But
That's great, thank you. I mean, I'm in maternal child health, so same thing. There's always a socioecological model.
yeah, right. That's true. It's very even like Rothenberger-esque. Yeah. Yeah.
It's Simon Vermeer, volume 12.
There you go. Anything else? Cool. Thank you.
Great.